Okay, part three. Um, let's see. Okay, so where we are, big picture, is we've learned these point process models, and we are in the process of being statisticians. We're starting with data, and we're trying to estimate useful things. We did that through the K function. We learned that the K function was not that useful for an inhomogeneous Poisson process. And the thing we want to estimate for an inhomogeneous Poisson process is that intensity function. So we imagine that the intensity varies with location, and we want to estimate it. And so that's the focus of this lecture. So there are two approaches. You can do a parametric approach or a non-parametric approach. I'm going to talk about the parametric approach first. The nice thing about parametric versus non-parametric, these are the usual choices we have to make when we're trying to decide whether we want to do something parametrically or non-parametrically. Parametrically, we get nice interpretability. We're estimating some parameters, and maybe those parameters are meaningful to us, particularly if we want to regress the intensity on some other covariate, elevation or something like that. Then that beta associated with the elevation could be meaningful to us. It does require us to make a model assumption. It requires us to put a parametric form on the intensity function, and so necessarily that's going to be less flexible than a non-parametric approach. So of course its advantage is that it's flexible. It has the usual bandwidth sort of selection issues. You have to choose a bandwidth. How much smoothing do you want to do? There are tools to try and help you with that assessment, but I think it often comes down to a modeling choice you have to make. They're less interpretable. A non-parametric model is going to give you an intensity at any location, but it might not have any parameters. It's probably not going to have any parameters that could be meaningful. So let me talk about parametric first, and then we'll do non-parametric later. So what I have here is a cartoon. What I'm trying to show is that we've got a higher intensity in the upper right than in the lower left. And we believe that the intensity function varies with location. We're going to call that location vector S. You can see I've scribbled out the X and Y. So if an X and Y appear in here, we'll have to make the translation from S to X and Y. But what we have to do is assume some parametric model for the intensity. And let's assume that we're going to just fit a linear trend surface. We're going to assume that the intensity varies with S1, it varies with S2 in a linear way. If we had our mapped data set and we saw that it appeared the intensity was higher up here, then we would imagine beta 1 and beta 2 are probably some positive number, and what we want to do is find the positive number that agrees with the data best. These, instead of doing linear trend where it's just a function of location, you could throw in other covariates that might be meaningful, like elevation. Okay, so our goal is to find the best beta naught, beta 1, beta 2 here. And we've got lots of estimation methods that we're familiar with from our other statistics classes. This seems like a regression problem, and so you might be tempted to think about least squares, but of course our data are locations in a region, and so it's hard to reconcile those locations. There are no numbers associated with these, so how do we reconcile the fact that I've got a point or an event at each of these locations? Method of moments, there's no underlying distribution that we know of that go with points. Maximum likelihood would seem to have that same challenge of what is the underlying density. It would be related to the count function, but it's unclear how you jump right to maximum likelihood. We are in fact going to do maximum likelihood, but it takes a little bit of development. So let's start with a definition of likelihood. And if you've taken STAT630, you've spent a lot of time thinking about what is a likelihood. This definition was pulled from the HarperCollins Dictionary of Mathematics, just because it was on my shelf whenever I wrote these notes up. That definition was that a likelihood is the probability of a given sample being drawn, regarded as a function of the parameters of the population. We, being a little more sophisticated, would be a little bit uncomfortable saying that the likelihood is a probability, but we're probably more comfortable saying that it's proportional to the probability. And that's kind of the way that I think it's presented in STAT630. So starting from there, can we get from what we know about a inhomogeneous Poisson process to something that resembles a likelihood? So you'll recall that the inhomogeneous Poisson process, the definition of it had two pieces. There was a third piece which we were able to prove, but we're only going to need these two pieces associated with the definition. Our count measure is Poisson distributed, where the mean of that Poisson is the integral of the intensity function over the region that you're applying the count variable to. So it's over the region A. And the second piece of the definition said that given that the number of points in A is n, then the locations of the points are independent and identically distributed with this PDF. So this is just looking at the intensity at a particular point S, and it's dividing by the integral of the intensity, which normalizes this, of course, and makes it a probability density. Importantly, the density is not uniform like it is in the homogeneous Poisson process, but they are independent and identically distributed. Okay, so let's think about our likelihood. Our likelihood, we're going to think of it as a function of some parameters theta. It's, going back to our definition, I think a place to start would be, say, this is at least maybe not equal to, but proportional to the probability that we observe endpoints in A. So we know what our points are. We're starting with knowledge of not only the number of points, but also their locations. So what is the probability that we observe endpoints in A and their locations are given by S1 through Sn? Well, we can go from this and probability statement to a condition, to a product of conditional probability. So that is equal to the probability that the locations are S1 through Sn, given that there are endpoints in A, times the probability that there are endpoints in A. Standard probability argument, but nicely, this relates directly to the definition that we were just talking about. This is part B of the definition. This is part A of the definition. And so we can write down a likelihood. This is pretty cool, I think, because we started with points. It's hard to see a density from points, and yet just starting with that definition of likelihood, we get something that makes a lot of sense. Part B of the definition, the locations are S1 through Sn, given that your endpoints, well, it's just going to be, because they're independent, it's going to be the product of those PDFs. So just lambda evaluated at the location, normalized by the integral of our intensity function. And then Poisson, the fact that we've got endpoints would be E to the negative value of the parameter, the value of the parameter of the n over n factorial. This is, of course, just our usual probability mass function evaluated for n, an account of n. So notice that we have n of these, and we have n of them up here, so those cancel with one another. And so we get the product of the intensity at the individual locations. Times, we still have our e to the negative stuff, and 1 over n factorial. Okay, so that's the likelihood. I can take the log to get the log likelihood. That I apply the log here, our product becomes a sum of log lambdas. The log kills this part off. I'm left with negative integral of lambda minus log n factorial, which of course is a constant. And so it's not a function of the parameters, so we can leave that off when we're maximizing our log likelihood. So I have this note that says, you know, when we jump to a parametric form, now what we're going to do is we're going to write our intensity measure as a function of our parameters. Here is our linear intensity model that we've assumed. We would need to enforce that our intensity measure is positive for all values in our study region A. And so you can imagine that we could find betas which would return a negative number for some S, and that wouldn't make any sense. We can't have a negative intensity. And so you might need to further enforce that restriction. But if I plug this in, then my log likelihood is the sum of the logs of this evaluated at the I location, well, at the n locations, I equals 1 to n, and then integrating my intensity measure over A. I'm going to assume that my study region is the square from 0 to 5. So you can see I'm doing that integral. This is just the integral of a polynomial. And so we get this expression for our likelihood. So again, I think this is pretty cool. I don't think it's very obvious of how we think of how we associate a likelihood with a point process, because there's no density that leaps out. And yet we can start with our fundamental understanding of what a likelihood is, tie that directly to the definition of inhomogeneous Poisson process, and get a likelihood. So let's actually do this in R. Okay, so here we are picking up from where we were before. I am writing down my negative log likelihood, so it's going to take a vector of betas. So this is going to be beta naught, beta 1, and beta 2, as I show here. The lambda evaluation is this is going to be in that sum of the log of lambdas. I just need to evaluate my inhomogeneous Poisson process is going to have a list of points with X locations and Y locations. So this is going to return lambda. I say that if any lambda is less than 0, return infinity. This is just enforcing that positivity constraint. And then let's see, so the first half is going to be the sum of the log of these lambda evaluations. The second half is going to be just that integral piece. So if you look at the notes, this directly corresponds with that integral. Sum up the two halves and return the negative log likelihood so that we are minimizing. So I enter that into memory. I'm going to generate my inhomogeneous Poisson process with that same trend that we were looking at before. Here is that guy. This is a little different than we saw in the last video where I did it on the square from 0 to 10. But we're still seeing some evidence of that inhomogeneity. We have fewer points down here than we do in the upper right. The true values are beta naught is 5, beta 1 is 20, beta 2 is 30. In line 372, I'm just showing you that if I give it values for the 3 betas, it returns a value for the negative log likelihood. Notice in line 372, I put in the true values of the parameters. If I put in different values for the parameters, my negative log likelihood performs less well because I've negated, we're trying to minimize. We see that we get a lower value with true parameter values than we would with these. So I can optimize my likelihood. I'm going to make it easy on myself. My starting values correspond to the true values. But of course, the estimates are going to deviate from that. The estimate for beta naught is 3.75. The estimate for beta 1 is 19. The estimate for beta 2 is 30.4. And so we can see that these are relatively close to the true values. If we wanted to get uncertainty estimates for our parameters, we could rely on asymptotic theory of likelihoods. I could get the Hessian with our likelihood surface, which is obtained right here. The diagonals of this Hessian are the estimated variance of our, actually of the inverse of the Hessian would be related to the variance. So that's what I'm doing here in line 380. And then to get the standard error, take the square root, and then asymptotic theory would say use a normal. So that's why I'm multiplying by negative 1.96 and positive 1.96 to get a 95% confidence interval. So our low estimate or the boundary of our confidence interval for beta naught would be from -4 to 11. Beta 1 would be 17 to 22. Beta 2 would be 27 to 30. And notice that the true values are inside each of those confidence intervals. Okay, so that is parametric estimation of intensity function. And I think, again, I just think it's really cool that we can get a likelihood for an inhomogeneous Poisson process. The disadvantage, of course, is that one has to assume a model, and maybe there's no intuitive answer for how that intensity should vary in space. So in that case, what we want to do is we want to do non-parametric intensity estimation. And basically this feels an awful lot like kernel density estimation. What we're going to do is we're going to pick a location, we're going to look at the concentration of values near that location, and we're going to do some sort of kernel estimate to get an estimate of the intensity. So for kernel density estimation, you of course have to choose some kernel. We're going to choose one where it integrates to 1, and usually you assume that it is symmetric. And in kernel density estimation, this is a terrible cartoon, but you imagine that you've got some points on a line, you throw some little kernels over them, and the estimate of the density is just the sum of the kernels at any location, not necessarily, and we get any location. It doesn't have to correspond with our data values. We get an estimate of the density in between the observed data. Our estimate of the overall density is just the sum of the kernels normalized by the number of points. And the reason we normalize by the number of points is that if I integrate this, I apply my integral, each of these is going to sum to 1, and so the sum is going to be n, and my kernel density estimate has an integral of 1, which is what we want when we're doing a density. But it's not what we want when we're doing intensity estimation. Our intensity is not a density in the sense that it returns a probability. What it returns is the expected number of points at a location. And so that expected number of points is not constrained to take on values between 0 and 1. It is constrained to be positive, of course, but is not constrained to be between 0 and 1. And so the only difference really is that we will do a kernel density estimation, but there's no reason to do this normalization. And in fact, if we just integrate over the whole region, we'll integrate this kernel, and what we'll end up with is n, which is our observed number of points. And so getting rid of this 1 over n makes sense. So that's what I'm saying here. Do we want the integral of our estimated intensity to equal 1? No. The right thing to do is just to get a kernel density estimate, but do not normalize by 1 over n. This has all of the usual challenges with that are true in kernel density estimation. If we choose a bandwidth which is too narrow, we'll get an estimate that is too wiggly. If we choose a bandwidth which is too wide, it will smooth things out. And so choosing that right bandwidth is something that must be done. And there are methods, cross-validation and such, to guide us in that choice. So let me just show this really quick. We're going to use a prepackaged tool in the STAT library, but really it really just is that same. What I've got is I'm using the density command. So if you've done kernel density estimation, you were thinking, gosh, you're doing a kernel density. If you give it something, an object that's known to be a point process, then the STAT library kicks in and it's going to do kernel intensity estimation rather than density estimation. But it still uses that density command. So there is my, I've done it. I didn't choose any bandwidth, so somehow there was an automatic tool in there choosing the bandwidth, and we can certainly look at that. Here is the density estimate for our inhomogeneous Poisson process, and not surprisingly, we're seeing it increase as we move from left to right and bottom to top, because this has that same linear trend. You can look at the help file and you can see, you know, that we've got tools that we can use this leave one out, because it's true, it's doing leave one out cross-validation to choose the best bandwidth. It's using some sort of edge correction, which you can imagine we would want to do, because the expected number of points as we get near the edges would drop off, because that kernel extends beyond the study region. Here, I'm just showing that we're getting a good estimate. I'm finding the point at which is closest to the center. The center of my region is at the location 2.5, 2.5. So this index is just which point is that closest value. So here is the point location 2.53. The ends at point. Oh, I forgot to run line 390. Dens out is our kernel density estimation. It is it's a function, so I can plug in any value that I want. Dens at point is plugging in the observed values. And so we're getting a density or an intensity measure, I should say, at 125 at this location near 2.5, and the true value, knowing that the true value of beta naught is 5, beta 1 is 20, beta 2 is 30. The true value is 130, and so we're seeing that we're getting a reasonable estimate of the intensity function. Okay, so oh shoot, maybe I was not sharing my screen there. Was I not sharing my screen there? Okay, it appears that I was not sharing my screen. Shoot. But just reviewing that, I'm using the command density for our inhomogeneous Poisson process. Here is our estimate of the density. We see it increasing as we go from left to right and bottom to top. I'm evaluating the density at that 2.5 location. I'm getting a value of 125, very close to 130. All right, that is all I have for today. Hopefully I will be back in class on Wednesday.